All right, good morning, everyone. My name's Liz. I'm from the Isovalent team at Cisco.
And I'm Neha Aggarwal. I'm Principal Engineer at Microsoft.
First of all, let me welcome you to my home city of London. How many British people do we have in the room today? Okay, so that number of hands is about the number of different opinions there will be about how to make a cup of tea. There are a lot of factors that can go into making a good cup of tea. Obviously, the brand of tea that you're using, whether it's a teapot or a tea bag, the kind of milk, milk first, milk second, even the kind of water, all these things affect whether you're getting a good cup of tea. And in just the same way that there are a lot of factors that can influence how you make that cup of tea, there are a lot of factors that can influence how you configure Cilium to behave for the performance and scalability that you need in your environment. So today we're going to talk a bit about some of those configuration options, some of the reasons why they're there, some of the ideas that are coming up for improving scalability and performance. And with that, I'll hand over to you to set the scene.
No, thank you, Liz, for all the tea inputs. I want to say in India as well, we have a lot of ways to make the teas, different ways, but we are tea lovers. Okay. So before that, how many of you have used ChatGPT to generate images over the weekend? we all know what we're talking about. Yes, right, the world is going crazy, isn't it? Filling up the social media. So we are in the new era of AI, which demands unprecedented scale. It is pushing the limits of network infrastructure, demanding higher scale, higher throughput with a very low network latency. And Cilium, being the de facto standard for Kubernetes network infrastructure, has to live up to the new standards we are creating. So Cilium, over the years, has built many great features. All of them are additive, and they're adding a lot of gains to the scale and performance. And they're building on top of each other. So it's all about how we tune the stack to get the most out of it. So let's learn about how we re-innovate the existing stack, build the new stuff out of it, and get the most out of it. Before we start on the new features, let's take a little quick recap of what Cilium architecture is built on. Very simple, Cilium has these node agents which are running on every node. They talk to the control plane API server to get some of the resource data, some of the CRDs it generates for provisioning of the pods, applying the network policies. So over the time, if your cluster scale is increasing, the load to the API server is increasing. So imagine if you have Cilium, for example, it generates Cilium endpoints, which is a CRD per pod. So if you now have 100 endpoints in your cluster, which is a 5K node cluster running, that gets updated, some of your big ticket workload gets updated. Now every agent which is watching these Cilium endpoints get 500K watch events in one go. So that adds a lot of pressure onto the API server, so like control plane pressure. Pivoting towards on the data plane, like if you have a pod running, there is a workload running on your node, it is traversing, the pod's coming up with its own network namespace. So it's traversing, so whenever the packet is leaving pod, it's entering into the host network namespace, adding an extra hop, adding TCP back pressure, and then leaving the traffic. So filling up the queues, and then resulting in retransmits and packet drops. So we are hitting some network back pressure on the data plane side as well. So moving on. So let's see how we can handle both control plane side of the scale challenges and as well as on the data plane. Diving deep on the control plane, like can Cilium agent, which is running on every node, reduces the pressure on the API server by reducing the watches and the list it creates on the API server load. Can we improve how we can improve the pod network provision SLA by reducing the load by reducing the CPU and memory load each agent is generating. So very first thing recently in Cilium, we built the Cilium endpoint slice. But before I talk about Cilium endpoint slice, let me share what is the behavior today. So today, as I was talking about the CRD Cilium endpoint, so Cilium agents, for every pod, they create this CRD Cilium endpoint, which is kind of a thin CRD, which carries the network metadata, like your ports information or IP information for Ciliums to provision the networking for the pods. So it generates, there's one Cilium endpoint per pod. Now, Cilium also applies policies, which are label-based, namespace-based. And for policies, you need both source and dest information. So every agent now has to watch all the IPs, all the Cilium endpoints of the whole cluster to be able to build this IP to identity, security identity map to be able to apply it to the policies. And that results in a lot of control plane pressure. So how we have reduced it by Cilium to create this feature called Cilium endpoint slices. How many of you have known Kubernetes endpoint slice, which was built for the kube-proxy? So it's built on the same premise. It's not the same. It's not a replacement of that. It's same idea, where we are batching the Cilium endpoint slices, Cilium endpoints into the Cilium endpoint slices. It's a smart batching, trying to package the Cilium endpoints, which is part of the same deployment, into that same slice, so that anytime there is a deployment update, you get lesser number of Cilium endpoint slice updates as well. Now, if you go to a little bit of a architecture where now Cilium agent, which we're watching all the Cilium endpoints, it's not anymore. It's a Cilium operator, which is watching the Cilium endpoints, generating these slices, and now every node agent is watching these slices instead of endpoints. So we've reduced the watch load on API server drastically. And some of the numbers I want to share, we have tested in our testbed performance benchmarks. So with existing, like on a 1K node with about 20K, around 20K pods, we saw a drastic drop of 87% reduced latency on the API server by using Cilium endpoint slice. And then there was around 60% improvement on the pod network SLA as well, increasing the pod create time. This Cilium endpoint slice is stable since from version 1.116 plus, so I highly recommend for customers who are facing scale challenges on the control plane side, a lot of pressure on the API server to leverage this. The second is this is also like it's very useful. It's there in the network standards, but it's not out. It's more of customers to use it. So going back to the network policies. So network policies are created. Cilium creates these security identities for your network policies. Now, security identities are created using the labels you apply on your deployments. Now, there are all sorts of labels we also apply, like which are used by customers, are not really used for security policies. But any label you add today, Cilium generate a security identity, assuming that you will be using it for your network policies. And that started to create a pressure on the Cilium agent to the amount of identities we generate. Some of the labels are very high churn, like timestamp based, or the UID, which keeps getting updated. And you don't want to keep creating the load on the Cilium agents to recreate those security identities. So we rolled out this capability where we can exclude some of the labels which are never going to be used by the Cilium network policies, exclude them out, and so that Cilium does not create those security identities, and reducing the load on the agents again. So try this out. There's a link to this doc that how you can include, how you can exclude. You can also define the configuration where you can define that this is my format of the label and only include this format of the label while generating the security identities. It's very dynamic and flexible. A little bit pivoting towards, we've talked about how we can increase the control plane scale for connectivity. But observability, what about observability? Observability kind of goes hand in hand with connectivity. So how do you achieve, while we're achieving your scale for your clusters, you want to make sure you are able to also observe at scale. So Hubble there has been huge investments happening in Hubble. Hemant mentioned in 117, we are improving Hubble performance, we are reducing the CPU. But at the same time, your number of workloads are increasing on your cluster. And so with this, recently there was the CFP added, where now we have added the support of dynamic metrics filtering. What it does is you can create your filter already for what kind of metrics you want in your Hubble observability, like DNS metrics, or I care about my TCP metrics. But today, there wasn't any way that I only care about DNS and TCP for my workload A. I don't care about these metrics for kube system namespace. Why should my Prometheus or Victoria metrics should be incurring the load for that? So with this CFP now, you can this CFPR is already in. With this, now we can even filter out that for this particular metric like TCP, just only use it for this workload namespace. So you can add the filters based on namespace and labels. So reducing by doing now the smart observability, I would say instead of observability at all, do smart observability to achieve the scale you want. So yeah, with that, I'll hand it over to Liz.
Yeah, so we've heard a lot about things that you can do on the control plane side to improve scalability and to improve performance at scale. But now let's think a little bit about the data plane side. So we think about data plane performance, we're really talking about how quickly we can get network traffic from where it started to where it needs to get to. We can think of that in terms of throughput, the amount of traffic we can move over a given period of time. We can also think about latency, trying to reduce the amount of time spent processing a given network packet. And there's always going to be a trade-off between processing a packet using CPU time for network processing versus using that CPU time for applications. You want to save the CPU for your applications. Data plane performance is also influenced by a lot of different factors. So the type of traffic that you're running, the size of packets, whether you're streaming or whether things are more request response, whether or not you are encrypting that network traffic. There's no single solution to optimize for all these different things. So for every given deployment, there will likely be different performance tuning that you might want to do. That said, are there things that we can do to minimize the amount of processing that each packet goes through? The more we can minimize the amount of code that a packet goes through, the likely improvement that's going to have on performance. So Neha already spoke a little bit about the fact that network traffic will pass through the network stack twice. We'll just talk a little bit about that, bring everybody up to speed on this. So in traditional container networking, we deliberately isolate the container, or in Kubernetes' case, the pod. We deliberately isolate the application from the host. We put it into a network namespace so that it is deliberately isolated from that host. But then that means we need to connect it, and we connect it using a virtual Ethernet connection, which is running, it's an extra network hop. So we've got things like ARP running between the virtual Ethernet pairs between the pod and the host. That means that every network packet, if we imagine it's coming in through that physical interface into the machine, it passes through the host's network stack. It then has to traverse the virtual Ethernet connection to reach the network namespace, where it goes through the network stack again before it reaches the application. And that was one of the things that I think inspired the idea of using eBPF for network traffic, that there could be things we could do to optimize this flow. We can now use something called eBPF host routing, which you can enable in your cluster to avoid a lot of the host network stack. So there's a helper function called BPF redirect peer that can take that network packet as it arrives into the host network namespace and switch it very quickly directly into the network namespace for the application where it's destined to go. And on the egress direction, so for traffic leaving the application, it still has to pass over the virtual Ethernet connection, but there is a helper function that can be used to look up the destination for that packet and redirect it without having to pass through all of the network stack on the host. So That, as you'll see in a moment, really does improve performance quite a lot, but there is still this virtual Ethernet connection. There is still queuing happening because packets are having to go on a CPU, per CPU queue to traverse that virtual Ethernet connection. There will be TCP back pressure across that connection. So there's still some overhead in this eBPF host routing. But it is a significant improvement. So in this chart, the right-hand bar, the dark blue bar, is host-to-host networking performance. This is throughput. And the left-hand paler bar is traditional container networking throughput. And you can see the middle bar, which is with eBPF host routing enabled, we get much closer to host networking performance. So that's a significant improvement. But, you know, the team that work on Cilium, the team that work on eBPF are not satisfied with that. So I particularly want to call out Daniel Borkman, who put Netkit devices into the kernel. And a Netkit device allows, it's similar to virtual Ethernet in that it has a pair, so there's a pair sitting in the network namespace for the pod, and a peer, a primary, sitting in the host network namespace. But the difference here is that the host, the primary, is allowed to manipulate eBPF programs inside the network namespace for the container. And that allows us to shortcut. We no longer need that virtual Ethernet connection. So we can pick up, we can have an eBPF helper function taking that packet directly from the network namespace as it kind of has left the application and switch it directly to the host network namespace with all the destination addresses and so on filled in. And that means we get no TCP, no per CPU queuing happening in either direction. So what does that do to performance? Well, it brings container networking performance to a par with host networking performance. Both in terms of the throughput and in terms of latency, we're basically seeing the same performance as we'd get if there were no containers at all. So eliminating container networking overhead. There's a link here to a talk from a KubeCon, a couple of KubeCons ago, that dives a bit more detail to the implementation of this, and also BIG TCP, which is the ability to handle really big network packets, which it means if you've got bigger packets, you have less time processing. There are fewer packets to handle, so less time required to process them. So I definitely recommend, if you want more detail, checking out that talk. Now, you might be wondering, why do we not just turn this on for everybody by default? And this is often something that people don't realize. The defaults are deliberately aimed at maximizing compatibility, maximizing or minimizing disruption to an existing cluster. So a lot of these features are not turned on by default. And one of the reasons you may or may not be able to use them is you may need particular kernel support in order to enable these features. I've just talked about Netkit. You're going to need a pretty recent kernel. It went into the kernel in version 6.8. Not a lot of people are using that recent a kernel in production today. And similarly, for a lot of other features, you may need kernel support. You may need support in your NIC driver for things like BIG TCP. And also, some of the performance improvements, these last couple here about tuning map sizes and how we measure time, let's say, you could enable them in a new cluster and you will almost certainly improve performance. But if you change it on an existing cluster, it will have disruptive effects to existing network connections on a cluster. So having chosen your performance settings that you're going to use on your environment, how can you test them? The good news is there is an easy-to-use Cilium CLI command, Cilium connectivity perf that we can use to test out how performance is running on a cluster. And Neha's going to show us it in action.
Yes, so we are having a live demo. So let's pray for the demo gods for this to work. So we're going to be showing, okay. So we're going to be showing how this Cilium amazing tool, which Liz was mentioning about Cilium connectivity perf, CLI works, and what kind of metrics you see, and it's like integrated into your Cilium CLI. So as you enable these tuning parameters to improve your scale and connectivity, like throughput, you can use this integrated tool to test, to measure it right away. So I'm going to start this tool because it's going to take some time, and then walk through where I'm running this cluster. Okay, so I'm connected to this cluster. It's the same cluster where the connectivity perf is running. So if you see, is it? Okay. So if you see the Cilium status, we have the endpoint slice. This cluster has the Cilium endpoint slices running. The connectivity perf is more on the throughput and your latency or response rate. So it's not really going to test the scale, but because we wanted to test all the features we talked about, we enabled the cluster with this, so you can actually see as endpoint slice CRD what it contains. It also has a routing mode, which is eBPF host route, which Liz was mentioning about that bypasses the networking stack on the host, and the device mode is Netkit. So there is no veth running on this cluster. These are Netkit device pairs. So let me just go back to the CRD. The Cilium endpoint slice. So let's see how a single endpoint slice looks. So yeah, I was mentioning about the Cilium endpoint slice, that it creates a batches of endpoints. So you probably would also see these endpoints as a separate CRDs. Like Cilium endpoint slice today contains you will see a batch of endpoints. You can create endpoint IDs, your name ports, IP information, all that which is in the endpoint, but you're getting that in one go. Like and you can configure what kind of batch size you want in your Cilium endpoint slices. Going back to your clusters which is running, let's see how the connectivity perf behind the scene is running. So I've connected to the Hubble UI, and currently your connectivity perf, what it has deployed a server, and then there are two client pods, one on the same node, one across the node, and it's sending the traffic to the server to measure your throughput across and on the same node, and hopefully very soon we're going to have the results, and we got the results.
Yes.
And so this is what the output will look like for your connectivity perf. You will have, it measures different scenarios. You have pod to pod, same node, cross node. You have pod to host, host to pod, to measure all the data across, measure your host performance, pod performance, and it has throughput. And I don't want to quote on the numbers because it's one time, so I would recommend this tool to be run multiple times to create the P99s and average out of it. So yeah. Okay. Yes. So. I'll go back to the slide mode. Yeah, so with this, we are on the path and the journey to achieve the scale which the AI is demanding, and we all are looking at you to contribute it more.
Yeah, there's lots of ideas that are being considered and worked on for further improving scale. I've collected a few of them here. You can look into the discussions going on. If you're interested in scalability, as was mentioned in the opening, there is a charter now for SIG scalability, so you can join Hemant and Marcel and the team working on scalability and get involved in some of these ideas and pushing Cilium to even greater scale and ability to perform for AI workloads and more. There is one very important rule about making a cup of tea, at least in my book. It's a very important rule. The milk must never touch the tea bag. Critical. I'm also going to say, if you want to see a fight between people from the UK, ask them how they pronounce the word scone and whether it's cream or jam first. I leave that with you.
Thanks for the great tip, Liz, because we Indians, I was telling Liz that we like to mix it together, like with the tea and the milk, and boil it, and then call it like a kadak chai. It's very different, so that's how the world works.
Great. Thank you. Thank you, demo gods. Brilliant.